Hello viewers, today we are going to design this truss and all the dimensions of this truss is given here. I will show you. This is the truss and the truss is given here. The base part of this truss is called tie. The incline, this upper part of this truss is called rafter. This vertical members are called strut and the inclined members here, those are slings. So now we will see the dimensions what are given. So let's see. So this is our truss and the dimensions are given. The span of this truss, the span that is given here as 14 meter, and the pitch angle that is given as 17 degree, and the diagram is given. The other things, those vertical length, those inclined length, that we have to calculate using this span and this pitch angle, or we can say roof angle. So we have calculated all those lengths of this strut, sling, rafter and each ties. Now, for designing, we have to calculate it, the loads for each trusses. For load calculation, at first we will calculate the dead loads. Including self weight, there are so many things that will be added in dead loads, like the weight of connection, weight of purlins, and the rope seating. Here for rope seating, we are using galvanium sheet. So let's see what we have done here in calculation. Okay, so the self weight of the truss is given as the span divided by 3 plus 5 whole into 10. What is our span here? That I have already told, that 14 meters. So using this formula I have calculated the self weight of truss, and this self weight is for a unit area, that is 96.67 Newton per meter square. Weight of galvanium sheet, that is also given 100 Newton per meter square, and we assume that weight of the connections is 100 Newton per meter square. So for each meter square area, the total load that is coming from truss, galvanium sheet and connections are 296.67 Newton per meter square. This is for unit area, and the load in each truss we have to calculate separately. So let's see how we can calculate. There it is written that the span of the truss, that I have already told, 14 meter, and the spacing of each frames means the this is a truss of an industrial building, so there will be so many n number of truss frames. So here we are using total 10 number of frame truss. There each frame is at a distance from one to another is 4.75 meter. And what I was telling about the purlin, that purlin weight we have assumed as 120 kilonewton per meter, but further when we will design the purlin, then we can exactly say what is the exact weight of the purlin. Now we are assuming as 120 kilonewton per meter. Okay, so for each truss there will be 9 number of purlins. How it will coming as 9? So you can see that upper nodes, there are total 9 nodes in the upper region. Here from left side it is 4, from right side it is 4, 4 plus 4 8, and the intermediate node, the upper node, that is 1. So total there is 9 node, and at each node there will be 1 purlin. So there are total 9 purlins. So there are total 9 purlins, and the purlin weight is given per unit length. So For the spacing that we have told that 4.75 meter for each spacing, what is the weight of purlin that we will to calculate. So that we will calculate as 9 into 120 means the 9 number of purlins, and weight of each purlin is 120 kilonewton per meter, and we'll specify the length, that is the spacing of two frame, that is 4.75 meters. So we calculated the load coming from the purlin is 5.13 kilonewton at each truss. Okay, so for each intermediate truss member, load due to above weight. So here the weight will be from the self weight, connection, purlin, and the roof seating, where we are using the galvanum seat. So except the purlin, we have calculated the weight per unit area, but we'll to calculate the exact weight in each truss. So we'll multiply with the effective area, that will give us the exact nodal load or load at each truss. So that is coming as 24.858 kilonewton, and the whole load is divided in this way in each truss. Like I have shown in this diagram, you can see that at edge points the load is P by 2, and the intermediate points there the load will be as P. So the total load is equal to 24.858, that is 8P. Total load is 8P equal to 24.858. So from there we can calculate the intermediate node load P, that is 3.107 kilonewton, and edge load, that is 1.5535 kilonewton. So by this way we have calculated the dead load. Now it's time to calculate the live load. The live load will be calculated in this way. So we have told or shown in the diagram that the roof angle is 17 degree, which is greater than 10 degree. The live load intensity for slope will be calculated like this. This formula we have collected from this IS code 875 part 2 1987. Let's see what is given there. Here it is written that I have already highlighted, for roof membrane sheet or purlins 0.75 kilonewton per meter square less 0.02 kilonewton per meter square for every degree increase in slope over 10 degrees. Means if the roof angle is 10 degree or below 10 degree, then the load will be as 0.75 kilonewton per meter square. But when the angle will be increased by 1 degree from 10 degree, then the load will be reduced by 0.02 kilonewton per meter square. That I have written as this formula, 0.75 minus 0.02 into alpha minus 10. So from there, using the value of alpha as 17 degree, we are getting 0.61 kilonewton per meter square. And the effective area that I have told during the dead load calculation, that is L into S. From there I will get the load intensity at each truss is 0.61 into LS, that is 40.565 kilonewton. So for similarly like dead load, we have calculated that 8 are equal to the total load. So 8P equal to the total load. Here we will similarly calculate the live load as 8 are equal to 40.565 kilonewton. So R is coming for intermediate node is 5.07 kilonewton, and for edge node it is coming as 2.535 kilonewton. So today we have done the load calculation. In the next video we will do the design in StatPro.